what do we still need to do? Yeah, we still need to check our answer, and we still need to solve for y, because after all, a solution is a coordinate x and y. And so far, we've only solved for x. So we need to solve for y. So where would be a good place to solve for y? Yeah, our substitution sentence is already set up to solve for y. So we take our -2. Now we write the substitution sentence empty for x. Notice that we have now written this equation empty for y, and now we're writing this equation empty for x. So we plug in our -2, and now we have y equals 10 minus 7, which is 3. And now right now we think the answer is -2, 3. At this point, we're neither right nor wrong. We're not done yet. So now we take our -2, 3 and plug it back into both equations. Now, in that case, this can just be chicken scratch for you. You can just look at it visually. You could just look at it and say, okay, that's 3 plus 5 times -2 is -10. 3 minus 10 is -7. That's true. And then 3, again, well, no, I'll go in order. 2 times -2 is -4. 3 times 4 is 12. -4 plus 12. -4 plus 12 is 8. Okay, so it works. So that really is the solution to the system of equations. This is the coordinate that makes both equations true. And what we talked about last time, which is so philosophically interesting, we now know that this system intersects at -2, 3. We have no idea what the lines look like. We don't know what direction they're pointing. We don't know if one's pointing down or one's pointing up. We don't know if they're pointing straight up or straight sideways. We don't know anything at all about what the picture looks like. But we know for sure they intersect right there. And that's really weird and interesting that we can know where they intersect, even though we have no idea about the nature of the two lines, what they actually look like. All right, so that was the substitution method. Now, how about elimination? Which one should we check, 8 or 9? Maybe 9, to make sure you got your whole numbers correct. So, number 9, we have 1/2 x plus 1/3 y equals 7/6. I'll stop right there. How do we get rid of all of those denominators? Because that's our goal. You would need the common denominator. So our common denominator for 2, 3, and 6?
6.
It would be 6. 2, 3, and 6 all go into 6. So if I multiply both sides by 6, I'm going to multiply all the sides by 6. Now, when you multiply by 6, what are you really multiplying by 6?
The divisor.
Well, the divisor would be the denominator. We're really multiplying the numerators by 6, right? When you multiply a whole number times a bunch of fractions, you're really multiplying all the numerators. So let's go ahead and distribute in that 6. That would give us 6/2 x plus 6/3 y equals 42/6. Okay, that could be the first step, is you just distribute that 6 to all the numerators. Then you go back through and simplify, so you have 3x plus 2y equals 7. So that's one of our whole numbers equations. How about the other one? Now the next one is 2/3 x plus 3/4 y equals 5/4. And once again, we need to find a common denominator for 3 and 4. Now let's just say that you're not sure what the common denominator for 3 and 4 is off the top of your head. Like you're looking at 3 and 4, and you're like, well, they both go into 24. They both go into a lot of different options. What's your fallback plan? Instead of thinking hard about what the least common denominator actually is, what could you do? What will always work? And instead of the least common denominator, you could just find a common denominator. What number is 3 and 4 guaranteed to go into? Yeah, 3 times 4, right? So instead of trying to really struggle to think what's the least common denominator, you can just find any common denominator by just multiplying the denominators all together. That would have worked here too. 2 times 3 times 6 is 36. I could have used 36. And that would have given me an equation in all whole numbers. So here, 3 and 4, I can just multiply them, say 12, and use 12. Now it just so happens that 12 is the least common denominator, but it will always work that you can just multiply the denominators all together, and that will give you a common denominator, and it will effectively work to cancel out all the fractions. So now what do we have? We have 24/3 x plus 36/4 y equals 60/4. And by simplifying that, we have 8x plus 9y equals 15. Is that what everyone got? All right, so I'm gonna write them above each other. So 8x plus 9y equals 15. What a great problem. So they're asking us to use the elimination method. Now, unlike the substitution method where you needed a substitution sentence, solving one equation for one variable, and then plugging it into the other equation, in the elimination method, what do we need?
A variable that cancels itself out, adding the two together.
A variable that will cancel itself out by adding the two together. And the only time a variable will cancel out is if what? It has to be,
Numbers.
the numbers have to be the same, but
One has to be a negative.
the signs have to be opposite. So, in this particular case, I either want both of these x's to be the same number opposite signs, or I want both of these y's to be the same number opposite signs. In this case, the technique I've shared with you is look at the bigger number, always look at the bigger number, like this is a plus 8x, and say, can I turn that into a negative 8x? And right now the answer is no, not conveniently. 3 times nothing will equal 8, not a whole number anyway. And then look at the bigger number, 9 plus 9y. Can I make this to be a negative 9y? Not conveniently. I mean, you could multiply by negative 4.5 if you wanted to. If you multiply times negative 4.5, you would get a negative 9. Okay, so then what do we do? If we can't turn the little number into the big number, we have to turn both numbers into a different number. And now again, you're asking, what's the least common denominator of 3 and 8? Or what's the least common denominator of 2 and 9? In this case, what's the least common denominator of 3 and 8? What's the smallest number that 3 and 8 both divide into? Yeah, 24. Now again, you'll notice you could just multiply 3 times 8 to make 24. So you can always just fall back on multiplying the numbers together and saying, okay, that's the number I want them both to be. Same thing with 2 and 9. The least common denominator happens to be 18, but that's also just the product. So you can always fall back on that and just say, well, since I can't make 2 into a 9, I'm just going to turn them both into 18. So let's do that with x, since it's over on the left there and we can see it better. I want to turn them both into the same number, so that's going to be 24. I need to turn that into 24, and I need to turn that into 24, but one of them has to be negative. So the bottom one, I'm going to go ahead and just make it into 24 by multiplying by 3. But the top one, I'll turn it into 24, but I'll make it a negative 24. So notice what we did. In order to eliminate the x variable, you can basically multiply the top equation by the bottom coefficient and the bottom equation by the top coefficient, and simply make sure that one of them is going to end up being negative and one of them is going to end up being positive. So we distribute all the way across. Make sure you distribute all the way across. That's why I draw these little lines to remind myself. So that'd be negative 24x minus 16y equals negative 56. Or distribute 24x plus 27y equals 45. So now I do get to add them together. The x's cancel out. And what is 27 minus 16? Is that 11? So it's 11y equals negative 11? Yeah, I think so. And then divide off the 11 and we get y equals folks, notice that we did a lot of work so far. And all that work was to effectively turn our equations into whole numbers instead of fractions, because they're easier to work with. And then to do our actual elimination step, where we had to turn both equations into a new number. And then finally, we now have y equals negative 1. So what do we still have to solve for? X. So then where do we get x from? What am I going to plug y into?
Whichever one you want.
Yeah, either one, whichever one you want. I'll probably choose this one because the number on x is smaller. I like choosing smaller coefficients because then I'm more likely to be able to do these calculations in my head. As opposed to dividing by 8, I'll just have to divide by 3. So I'll now take 3x plus 2y, writing y empty, equals 7. And in for y, I put negative 1. So then I have 3x minus 2 equals 7. And then moving the 2 over, moving the 2, 3x equals 9. And then divide by 3. Okay, and I get x equals 3. So at this point, we have x equals 3, y equals negative 1. We think the answer is 3 and negative 1. At this point, we're neither right nor wrong. We're just not done yet. Run number 9, just so you know. Okay, so then we check. Now, this is a little less exciting to check. How do we check? Can we plug 3, -1 into these? I mean, yeah, you can, but the best bet is always to plug your solution into the original system. Because after all, even by now, right here, we could have made a mistake in converting these fractional equations into whole number equations. And plugging our answer into here just means that this solves this system. But if we made a mistake in converting our fractional system into whole number system, then we wouldn't know that by just plugging this into this one. We have to plug it back into the original in order to know for sure that you really did find a solution to the original. So how are you going to do all those calculations with fractions? You can either just write them down. So what's our solution? 3, -1? So you can just go and write down the equation again. So that's 1/2 plus 1/3 equals 7/6. And then we have 2/3 plus 3/4 equals 5/4. And probably what I would do, so that's 3 and -1, 3 and -1. If you're feeling up to the task, you can do all this fraction work on paper, you know, in your head or on paper, or you can plug it all into your calculator. But folks, if you do plug this into your calculator, what do you have to be darn sure to do with these fractions? Put what? Put what, Brendan?
Put them in parentheses.
Yeah, you have to put them in parentheses. So when you type this into your calculator, folks, it would have to look like this. Parenthesis, 1 divided by 2, parenthesis, parenthesis, 3, plus parenthesis, 1 divided by 3, parenthesis, -1. And then see if all that equals 7/6. Right? And then here again, it would be 2 divided by 3, parenthesis, 3, plus 3 divided by 4, within parentheses, parenthesis, -1. Folks, I can't tell you how many times I see a student come up to me with their calculator, and they have it typed in like this, and they say, I've tried the problem 10 times, and I keep getting it wrong. Oh, you're not using all the parentheses. So the parentheses are really important that those fractions get wrapped up in parentheses. Every fraction should always be in a parenthesis. So did we get the right answer? Did anyone check? Oh, we did? Okay, great, thanks. Alrighty, so that's substitution, that's elimination. Both are just splendid methods for solving a system of 2 equations. And so we can move forward here. Let's just review that vocabulary we mentioned the other day. Consistent, independent, consistent, dependent, and inconsistent. So what do these words mean? I suppose I'll put it back here on my note page. So for consistent, independent, that was a solution, a system that actually has a solution. Consistent meaning you can find the answer, and independent meaning that there's just one of them. Whereas consistent dependent is a parallel system, meaning again you can solve for x and y. There are points where they intersect. So consistent means there are points of intersection. Independent means there's just one of them, and dependent means that there's infinitely many of them. Whereas inconsistent means there's no solution. And that's because the lines are parallel. This is just a vocabulary that the book uses, as well as the online website more. I've never been a huge fan of this vocabulary because I just like saying what the system is, like intersecting, overlapping, parallel. I think those are really nice descriptions. So in number 10, 11, and 12, they would like to know what type of system it is. They're not necessarily asking you, well, no, I guess it does say solve by substitution or elimination and then classify. So how about just for us, we'll go ahead and just classify. How could we just classify these? We could just graph them real quick and just see what happens, right? This would be a really good time for you to practice on your graphing calculator. Take out your graphing calculator and try plugging these in. Let's just talk about how you would plug these in, okay? When you go to your graphing screen, which you push the y equals button, and then you're going to have y1, y2, and so on. You have to type it in correctly. And the only way you can type these in your graphing calculator is by first solving for y. So let's talk about solving for y real quick. Let's look at that first equation. X plus 2y over 4 equals -5. You can't plug that into your graphing calculator the way it is. What do we have to do first? What is it? Yeah, multiply by the 4, and then subtract over the x, and then divide off the 2. We have to completely solve for y. So let's do that. So if I multiply both sides by 4, thanks, Jackie, we get x plus 2y equals negative 20. And then move, quote, move over the x. So now 2y equals negative x minus 20. And then divide by 2. Folks, when you divide by 2, you're dividing everything by 2. So it'd be helpful to draw a bunch of separate fraction lines. So now what we have is y equals, now what's negative x over 2? Again, we want to talk about the right way to type this into your calculator so you actually get the right answer. What's the number on x?
1.
A 1. And 1/2 is really 0.5, and it's a negative. So probably it'd be easiest to type in negative 0.5 x. Like the decimal would be easier than typing in parenthesis 1 divided by 2 parenthesis as a fraction. And then 20 divided by 2 is 10, so that's minus 10. So there's your first equation. Now go ahead and do the same thing with the next one. 3x minus y over 2 equals 1. And solve for y. Just a real quick friendly reminder, if you're going to solve for y, what should you do to y first? Do what?
Get y.
Well, correct. We want to get y by itself, but what should I put in there real quick? Yeah, put a 1 on there. Anytime you have a variable with no number, put the number there. It's a 1. Okay, everybody, go ahead and solve for y in that second one. Get it all the way down to solving for y. And once you have your So you move it to over here, and then you minus the 3x, and then you divide by 9. Yeah. Once you have both of those y equals, now you can go ahead and type them both into your calculator, and we can actually check and see what the system should be. So on this one, you multiply both sides by 2 to cancel out that 2. 3x minus 1y equals 2. And then you subtracted the 3x. So then you have negative 1y equals negative 3x plus 2. And then you divide everything by negative 1. What can you do besides dividing everything by negative 1? Yeah, you could have multiplied everything by negative 1 as well. Remember, we now have this new trick up our sleeve, which you can take any equation and just change all the signs all the way across. So instead of the equation negative 1y equals negative 3x plus 2, think you have 3 different options. You could divide with negative 1, or you could multiply negative 1, or you just change all the signs. Right? That's just something you can keep in mind. I'll just change all the signs. And changing all the signs is the legitimate shortcut to either dividing everything by negative 1 or multiplying everything by negative 1. Okay, so what are our 2 equations that we're going to graph? In your calculator, it's going to be 3x minus 2 and negative 0.5x minus 10. So go ahead and graph those on your calculator. And I'll walk around real quick to help everybody with their calculator if you have any questions about getting it in there. So let's see, this is 3x minus 2. And negative 0.5x minus 10. Now, again, everyone try it on your own calculator. See if that point of intersection down there in the lower left-hand quadrant, is that where it graphed? So on your calculator, depending on your calculator, you now have to ask your calculator, what is that point of intersection? Desmos is nice, it just gave it to me. On your calculator, though, you would have to go to second calc, so second trace. Let me hold up my calculator. Now that you've typed it in, you would have to go second, which is that option button, and then trace. So really you're choosing second calc right above it. And then once you go into second calc, the 5th option is intersect. Well, one of your options will be intersect. And so when you choose intersect, it's just going to go ahead and ask you, choose the first curve, choose the second curve, and then hit enter to find it. So go ahead, you basically just hit enter 3 times in a row and see if that works for you. Did it work? Yeah. Yeah, verify that your solution is the same as mine, -2 something and -8 something. Let me know if it didn't work for you so I can come around and help. Where's your other one? Oh, okay. Did everybody get a graph? Brandon, did it work out for you?
I just did on that.
Okay, that's perfect. Gotcha. Very nice. Did it work out, Josh? Hey, great.
I know how to.
Okay, super. Okay, so we all have an answer. Now, in terms of just answering this question, what kind of system was it? Consistent, independent, consistent, dependent, or inconsistent? Yeah, it's a consistent independent, so we have that. Now, the only tricky thing is that your calculator and Desmos has only given us a decimal approximation. And so right now, we have no idea what the real answer is. Now, you'll notice Desmos only gave me 3 decimals. What can you do with 3 decimals? Nothing! You can't do anything with 3 decimals. Not to mention the fact that they're rounded. The last digit, well, that is actually 7, but I don't think that that decimal is correct. I think it's rounded. Anyway, right now we have no idea what the real answer is, do we? Even if you had your calculator gives you more decimals. I'm going to borrow Abe's. They're what?
They're both rounded.
Yeah, they're both rounded. So the solution that I see on Abe's calculator is -2.285714, and then -8.857143. So what's really tricky here is that now we don't know what the actual decimal answer is, right? I'm sorry, not the decimal answer, the fractional answer, because the fraction is the real answer. A decimal is always an approximation, right? A decimal is always an approximation. So if you just needed to type in a 4 decimal answer into more, we could do that right now. So you could round this to 4 decimals and you could be done. But how do you know what the actual answer is? What's that, Chelsea? Yeah, you'd have to actually solve it, right? Or by sheer dumb luck, if you happen to know that the decimal expansion for 1/7 is 0.142857142857, you would say to yourself, hey, 28514 and 857143, I see the digits here. If I actually continue this one, it's 0.285142857. So that looks like it's some fraction relating to sevenths. And then this one also is 85714. That 3 is really a 2, 857 repeating. So both of these numbers are somehow dealing with a fraction of a 7th. And what you can do now that you know how to continue the decimal, everybody try this, super fun. Go to your main calculator screen. Go to your main calculator screen and everybody start typing in with me. Negative, you're just typing it into your regular calculator screen. Negative 2.28514. And at this point it continues 142857. 142857. Do it 3 or 4 times. 142857. 142857. You're giving your calculator enough repeating decimals so that it can make an inference about what fraction you're actually looking at. So if you type that in quite a few times, 142857, and then hit math frac, it'll actually give you an answer. Right? But you have to give it enough decimals for it to actually know what's happening. Now, to tell you the truth, I'm looking at this answer now and I'm not having a lot of confidence in it. I suppose it's possible that I made a completely incorrect assumption about all this, that the answer would come out to be some sort of sevenths.
They were fractions, but
Yeah, that doesn't look right. That was a leap I was taking. I was taking a leap that these were continuations of the decimal expansion of 1/7. I could be wrong.
I got a third from
You got what?
it was like X was 8.666 and then Y was like 10.33. So like 30 over 3 for Y.
Wait, are you saying these decimals are wrong?
When I originally solved for it,
Yeah, I suppose at this point we would actually need to know, did everything that we just do, was it correct? I mean, did we even solve those equations correctly?
I thought I would.
If I have y equals 3x minus 2, and then y equals negative 0.5x minus 10, we could go ahead and solve the system by plugging this in for y. So that's 3x minus 2 equals negative 0.5x minus 10. So then adding my 2 over, and adding the 0.5 over, oh, this is promising. Then we would have 3.5x equals 10. And so x equals 10 over 3.5, which is really 100 over 7. And let's see what 100 over 7 is. Oh, but that's not negative. Weren't we expecting both of these to be negative? Oh, but that's a 2. Oh, that's a 2. That should be negative 8. That should be negative 8. That should be negative 16 over 7. And now let's see, 16 divided by 7. Oh, thank goodness, that is the 2.28514. Why did that not work out? Because I typed in a typo. Geez, negative 2.28557. Where did I get those incorrect numbers from? Where did I type these down from? My calculator? Your calculator? Where's from? Well, that's strange. Yeah, this is actually correct. Okay, so yeah, it was a fraction relating to 7, but somehow this was not the right numbers. Did I see your calculator? Yeah, negative 0.5x minus 10 and then 3x minus 2. Well, gee, what is that? Should have totally worked. That intersection point again. First group, second group, yes. Negative 2.285714. Abe, I just didn't type down all the numbers. And negative 8.85714. Okay, everything I said should work. I had one number down incorrectly there. So now, if I do type down negative 2.2857142857142857142857, and then math racket, it does give me the correct answer of negative 16/7. And then the other one would be negative 8.857142857142857142857. And then I'll math rack that one. And that's negative 62/7. Okay. That was a lot to think about. I was attempting to show you some graphing calculator techniques. The first one was, let's go back to the beginning here now that we have it all down. The first idea was just take your equations, solve them for y, and graph them on your graphing calculator so you can actually see the system. And there, well, we saw the system, and it intersected once. The next idea was to use your calculator to get a decimal, but a decimal is not giving you the full the full fractional answer. So one thing you could always do is use your calculator to hit math rack, but that's only if you know enough of the decimal expansion. And this is kind of random, like whether or not you happen to know the expansion of 1/7. So really what you'd have to do is just fall back on solving the system. And if you solve the system, you will in fact get the actual answers. That first one was negative 16/7. There we go. Okay. So for the next two problems, again, I just want us to see what kind of system is it. So let's go ahead and do the next one. We want to solve both of those equations for y. So in number 11, how do we solve this first equation for y? What is that? How do we go ahead and solve this for y? What would be a good first step? Get rid of the fractions, absolutely. And to do that, you can find the common denominator, or you can just multiply through by the product of all fractions. So, the denominator. So 2 times 3 is 6, so we're going to multiply all the way through by 6. So that would give us 6/2 x minus 6/3 y equals 6. Don't forget to multiply the 6 times the other side.
Should be -6. It's a negative.
Oh, thank you. Negative, negative. So that gives us 3x minus 2y equals -6. We're not done solving for y yet. Remember, you're trying to solve all the way for y so that you can plug both of these into your graphing calculator. So now we proceed to solve for y. We move the x term over, and negative 2y equals negative 3x minus equals 3/2 x plus 3. Now that 3/2, when you type it into your calculator, you could either write y equals parenthesis 3 divided by 2 parenthesis x, or you could just convert that to a decimal and say 1.5x plus 3. And we did all that just so that you could take that first equation and type it into your graphing calculator. So now we still have to take the second equation and solve that for y. The second equation is a lot easier to solve for y because there weren't a bunch of fractions that you have to get rid of. All right, so the second equation, we can just move over the 3x and get a 2y equals 3x plus 6, and then divide everything by 2. We get y equals 3x plus 3, which again is y equals, if you want to type it in as a decimal, 1.5x plus 3. Now, do we have to graph this system? I mean, you could go ahead and plug both of those into your y equals. But what do you notice about the two equations you're about to graph? They're identical. They're the exact same. So this system is obviously going to be overlapping. So we already know it's consistent, dependent, it's overlapping. There's infinitely many points of intersection because they are the exact same equation. So that's kind of nice. I mean, we still did a lot of work, didn't we? We had to get rid of the fractions, solve for y, solve for y. We still did a ton of work. We just didn't actually have to solve the system. We didn't actually have to do substitution or elimination or graphing to realize that these are overlapping lines, which means there's infinitely many points of intersection. All right. So we have one more system to go. Number 12. I'll leave that there. So number 12, we've got 5, 6, x plus 5/3 y equals 7/3. And then negative 10/3 x minus 20/3 y equals 10. So you'll notice that what we're doing right now, folks, is just good algebra. This is a really good review of algebra. So when you see an equation like this, what's your first thought? My first thought is I'm going to get rid of all the fractions. Let's get rid of all those fractions. So again, now, folks, what's the common denominator of 6, 3, and 3? 6, right? Because 3 goes into 6, so you're already done. But just so you know, if you just took 6, 3, and 3 and multiplied them all together, so 3 times 3 is 9 times 6 is 54, you could go ahead and use the number 54. All right, that's like your fallback. Like, if you're not sure what the least common denominator of 3 denominators are, you can just multiply them all together and use that number. And that's nice because it gets the job done. The number is just bigger than it has to be, right? So you're exchanging the effort it takes to find a common denominator for the effort it will take to use larger numbers, right? So it's a trade-off. But in this case, yeah, the common denominator is 6. So again, you're multiplying all the numerators by 6, so that gives you 36x plus 30/3 y equals 42/3. So then that's 5x plus 10y equals something. And then 14, thanks. And then over here, we also want to get rid of these fractions where the least common denominator of 3 and 3 is just 3. But again, you could do 3 times 3 times 1 is 9 and use 9 if you really wanted to. That's your fallback. But I'm going to use 3. Now, what can I do instead of actually multiplying the 3 times the 10? Because you do see that there's a 3 down there, so that's going to cancel. So it could be that when I multiply the 3 here, it just cancels the 3 and it gives me negative 10x. And then when I multiply the 3 here, it just cancels the 3 and gives me negative 20y. But when I multiply the 3 here, it doesn't cancel with the 1, so that really is 30. If you like that, of course you can do that. You can cancel as you go. But it's probably better just to distribute to the numerators and then cancel afterwards. Okay, I'm going to write our two systems on top of each other. 5x plus 10y equals 14. That's our system in whole numbers. Do we have to now proceed to solve both of those for y in order to graph it? I mean, you don't have to. We were just using graphing to verify that everybody knew how to use your calculator to graph. But the question still is just asking what type of system is it? We could just go ahead and solve the system, and that'll tell us what kind of system it is. And this is already ready to go for what system, I mean, it's pretty close to being ready for what? Substitution or elimination? Yeah, elimination would be pretty easy here, because I can turn a 5 into a 10, or I can turn a 10 into a 20. Did I miss that? Yeah. Oh, that was a negative 7/3. Thank you. Thank you. All right. So I would say instead of graphing, like solving for y on both of these would be timely. You know, it'd be time consuming. Whereas right now I could just go ahead and do elimination. So looking at the x, this is a negative 10. I want that to be a positive 10. So I can go ahead and do that. I'm just going to multiply this whole system times 2, or that equation times 2. So now that's going to give me 10x plus 20y equals negative 28. And I'm going to rewrite the top equation right below it. And now look. What's about to happen? The x's cancels, the y cancels. And so I have something equals 2. What do I have over here? 0. All right, well, this is wonderful. We ended up with a false statement. So again, remember, that's like we said, where do these lines intersect? And the answer came back false. Meaning, where do they intersect? Yeah, they don't. They never intersect because they're parallel. And so what type of system is this?
Inconsistent.
Yeah, this is inconsistent. So the next time you're arguing with a friend and you want to insult them and tell them that they're inconsistent, you can just be like, it's kind of parallel right now. Then they won't really know what you're saying to them, right? They'll think you're complimenting them maybe. Okay, well folks, now we get into the good stuff. We're about to do some word problems with systems, and then we're going to start solving three equation, 3 variable systems. This is fun. And we'll solve a couple of word problems with those, and maybe that'll be the end of today, and then the next time we come in, we'll do matrices. No, I bet we'll get into the matrices as well. Okay, so we're about to start number 13. It's a word problem. And if you recall, we had a 2-step process for turning a word problem into an algebra problem. So I gave you 2 steps last time. What were the 2 steps? How to convert a word problem into an algebra problem. And this holds generally true, right? So to convert words into algebra. What was step 1?
Define your variables.
Yeah, define your variables. And where do you look to know what your variables are going to be? How do you know which variables to use? Where do you always look? Yeah, whatever the question is. It's typically the last sentence in the word problem, there's a question. And that question tells you what the unknown is. And whatever that unknown is, that's your variable. And then the second step? Yeah, you create your equations. So we're about to do that in these word problems. So the first thing we'll do is we'll define our variables by looking at the question and identifying what the unknown is. And then we'll go about creating our equations, create equations. So let's look at number 13. A local buffet charges $7.50 per person for the basic buffet. Sign me up. $7 for a buffet, not bad. Now, is it going to be a good buffet? Maybe, maybe not. But it sounds good to me. So a local buffet charges $7.50 per person for the basic, and then $9.25 for the deluxe, which includes crab legs. Now again, $9.25 for a crab leg buffet. This might not be the best food, but what the heck, you know? Just go anyway. You'll have a good time. Now, if 27 diners went out to eat, diners, that's talking about people, right? A diner is also like a local diner, like a small town has a diner. But in this case, they're referring to a person. So a diner went out to eat, and the total bill was $227. So again, 27 people went out, and the bill was $227 before taxes, assuming none of them ordered drinks or soda. How many chose the basic buffet, and how many chose the deluxe buffet? Yep. So that's the question. Does the question make sense? How many people went out to dinner? 27. How much did they pay? 277. Those two things right there are going to determine our two equations. Right? We're going to create equations. One equation will be about the total number of people, which is 27. And the other equation will be about the total number of money, which was 227. So that tells you what equations you're going to create. So let's start defining our variables. So step one, define variables. In mathematics, we typically start by writing the word let. So let x equal what?
Basic buffet.
Yeah, the number of people that chose the basic buffet. So you could always just say x is the number of basic buffets. But remember, we're talking about people, right? It's the number of people that chose the basic buffets. Probably be better to write it out completely so that we all know, including your audience, number of people who chose basic. See, there's a trade-off. It takes a little more effort to write down a specific variable in the beginning. You're like, oh, I don't want to write all that down. But later on, when you're all done with the problem, it's really helpful to be able to go back and see what the heck x represented. And then you're not like trying to translate what you wrote before. So y equals number of people who chose the lefts. Then you can get away with just using some quotes. Okay, so those are our variables. Now what do we do? Typically, every piece of information they give you is going to be an equation. So the first piece of information they gave us was 27 diners. That's the number of people. So everybody, let's say that. Our first equation is the number of people. So what would that equation be?
X plus y equals 27.
Yeah, x plus y equals 27, right? Now, folks, kind of like the more you write down, the better it is for your brain and for your audience. Like, was that helpful that I wrote down that the first equation would refer to the number of people? I mean, I think it's helpful. I think it's better to specify that so that you know what you're trying to build. So therefore, the second equation is talking about a number. The other piece of information they gave us was that it was $227. So now the second equation is the total cost, which means it's some sort of equation that equals 227. All right, again, you'll notice that both of the equations end up equaling the two pieces of information they gave us. And you might say, Mr. G, they gave us more information. They told us it was $7.50 for basic and $9.25 for deluxe. But that's just cost information that we need to use to build our equation. The actual two equations are built out of the information that they told us that there were 27 people and the bill was 227. Okay, so now how do we finish this equation? Yeah, it's going to be 750 times x, because for each person who chose the basic buffet, for each person, you have to multiply times 750, because that's the total amount of money that was spent. And then 925y, because y is the number of people who chose deluxe, and 925 is the cost of the deluxe. So now we have our two equations. So again, we haven't even solved the system yet, but what we just did is a skill in and of itself. Just the sheer ability to read a word problem, to identify the question, identify the variables, identify the information they gave us, create equations, and label the equations so that you and your audience all know what these things represent. So what method would be best? Substitution or elimination? Yeah, maybe substitution. I could see that half of you might say substitution, the other half might say elimination. Because with substitution, it'd be pretty easy now to just solve for x or y. Neither of them have a coefficient on them. So I could go ahead and do substitution. And using substitution, my substitution sentence could be, let's say, x plus y equals 27, move over the y. And now I have x equals negative 1y plus 27. And that's my substitution sentence going into the other equation's x, 7.5x, plus 9.25 y equals 227. So that would be if you want to do substitution. But how could you set it up for elimination? Elimination would be just as easy, right? Because for either variable, let's say x, if I want to eliminate positive 7.5x, I wish this would be, this one's already positive 7.5x. I want this to be negative 7.5x. So I could always just multiply negative 7.5 times x plus y equals 27. And distribute that across, and that would be negative 7.5x minus 7.5y equals negative 202.5. And then write the other equation right below it. And then you could eliminate the x. So everybody, you can choose. You know? I bet half of you choose substitution, half of you choose elimination, and just choose one of those two methods and go ahead and solve the problem. Everybody choose whatever method you're most excited about. I got you started on the board. Either do substitution or do elimination. Now, I know I've said in the past that if you have two methods to solve a problem, which one should you choose? Both. Because that way you can check that both methods give you the same answer. But in the case of algebra, you can check your answer by just plugging it into the original system and making sure that it's true. So it's not like you have to do both, because one method should be enough. One method should give you an answer that you can check by plugging the answer in, and if it's true, it's true. Which one did you try? Substitution?
Yeah.
Oh. Oh, yeah. You know what? Which way did you try? Oh. Which way did you choose? Substitution.
Well, when we move to the y over, it should be negative y plus 24. Or negative y plus 27, that's 7. Yeah, so those two got switched.
I'm seeing a lot of people with y equals 14. It's lending support to the possibility that the answer is y equals 14. Let's do a substitution. And so if y is 14, then x should be 13. So let's see. If you wanted to do substitution, you can follow along up here, negative 1y plus 27. Now keep in mind, I like to write negative 1y plus 27, but some of you wrote 27 minus y. You can write 27 minus y. I just like to put the variable first, negative 1y plus 27. So I distribute, and so I get negative 7.5y minus 202.5, definitely need your calculator for that, plus 9.25y equals 227. And then I can cancel, well not cancel, but combine like terms for those two, so that'd be $1.75y minus 202.5. Was that correct? Is it 1.75?
Yeah.
And then add over the 202.5. Oh, this is not looking good. I must have made a mistake. Oh, because that's positive. There's my mistake.
I made the same mistake.
Yeah. All right, there we go. That's much better. So now we have 1.75y equals 24.5? Is that it?
Yeah.
Okay. So then dividing off by the 1.75, that gives me y equals probably 14. Great. Okay, so at least in the substitution method, I got y equals 14. And that's only because I solved for x. Some of you might have solved for y. And if you had done y equals negative x plus 27, you would have just solved for x. Okay, now that I know y is 14, it's very easy to know what the other answer is. Because we have this very simple equation. If you add them, you get 27. So if that's 14, the other one must be 13, because they add up to 27. Or if you did elimination, the x's already cancel out, and I get 1.75y equals 24.5. Folks, what do you notice about the elimination method and the substitution method? True. And what else? Where do they both take you? They take you to the exact same equation step. They both lead you to 1.75y equals 24.5. It just depends on how you got there. Yeah, it does appear that in this case, substitution was the much longer method to take. Okay, so then you divide by the 1.75 and you still get y equals 14. Yep. Yeah, it does look like elimination was the easier. Well, you know, the word easier really depends. It depends on how easy you find it to set up the equation so that you can eliminate, right? Because sometimes it takes a lot of effort to set up the equation to eliminate.
I was gonna say, it's like mostly the same steps, but it's visually easier.
Yeah, they are mostly the same steps. It all just depends on your comfort level. You know, just depending on the equation, you might choose elimination, you might choose substitution. All right, well, so are we correct? What do these things mean? Y is the number of people who chose deluxe, and X is the number of people who chose basic. And checking our answer, sure enough, how many total people were there? 27. So there's that check. They do add up to 27. And then how do I check that the total is $227? You actually have to multiply it out. So the basic dinner was $750, so times 750. The deluxe dinner was times 925. So I'll take my calculator and actually plug in 14 times 925 plus 13 times 7.5. And that gave me a total of $227. So in both cases, it works out. There were 27 people and it cost $227. Okay, so we have a couple more word problems, and then we'll switch to 3 variables. But let's go ahead and take our break. The time is 9:06. Let's come back at 9:16.
Okay, I came in last Tuesday and the medication was gone. I had some side effects with, so I was really scheduled.
All right, it's 9:16. A few people are outside. Let me go get them. All right, so let's try the same thing with the next one. And I think what we'll do, oh, I didn't want to do that. Oh well. What we'll do is we'll focus on setting up the problem. Setting up the problem. So I'll leave that up there for a second. And number 14 says, at the old home filler up and keep on trucking cafe. Sounds tasty. The old home filler up and keep on a trucking cafe. Now I'm very confused. Does that mean an old home? Like the old home? Or like for old people? I'm not quite sure. Like the old person's home? No, I think it's just the old, as in like OL apostrophe, like the old home filler up and keep on a trucking cafe. Mavis mixes two different types of coffee beans to produce a house blend. Okay, so what are we talking about? We got a cafe, a person named Mavis, boys, girls, do we know? I don't know, maybe it doesn't matter. And mixes two different types of coffee beans to produce a house blend. So the first type of coffee is $3 a pound. Wow, do any of you buy coffee by the pound, by the way? $3 per pound is incredibly inexpensive. Normally, if you go to like Safeway or a grocery store or Sprouts, coffee beans by the pound are like $7, $8, $9. And then the second one is $8 per pound. So how much of each type does Mavis use to make 50 pounds of a blend that costs $6 per pound? Okay, so let's just imagine here what we're talking about. So this is number 14. What we have is this person named Mavis. I suppose it doesn't matter that I write down their name. And on the one hand, they have a bag of coffee beans, and that's $3 per pound. And then on the other hand, Mavis purchases another bag of coffee beans, which is $8 per pound. And then what Mavis does is pours a little bit of each into a new bag, which costs $6 per pound. Okay, does that sound reasonable as to what we're talking about? Yeah, and the question is, how much of each bag is Mavis pouring in? Like, is it a lot of the $3 a pound and just a little bit of the $8 per pound? Or is it mostly $8 per pound and just a little bit of $3 per pound? Or is it a fairly good mixture of each? So, could we take a guess as to which one of them she's using more of? She heard here. What? Maybe the $3 pound? What makes you guess that? Oh, well, that's a good point. I mean, if she was using a ton of the 8 per pound and only charging 6, then yeah, she's losing money right off the bat. She's not even making money by selling coffee. So yeah, you'd think that if she's selling it at $6 per pound, hopefully it's mostly $3 per pound so that she's making money. So yeah, we hope she's using more of this. But now how else can we check? That was just a hope based on profitability. Maybe she doesn't care about making profit on coffee. Maybe she's okay with making no profit at all on coffee because she's going to make the profit on the food that she makes. So that's just a guess. Oh no, I'm sorry. This is supposed to be silenced. There we go. Ooh. Okay, but how else could we guess? What if she used equal parts? That's always a good starting point. What if she just used equal parts of each? How much would it cost if she just blends equal parts of each? what would you do with the 3 and the 8? You just add them together and divide by 2, right? Basic averaging, taking the mean of the two numbers. So if I did do 3 plus 8 divided by 2, that'd be 11 over 2, which is 550. So if she straight up just mixed the two bags together, the cost would be $5.50 per pound. But the fact is, it's $6 per pound, which is slightly more than $5.50. Therefore, which bag is she using more of? Since the cost is a little bit more than the average, which bag is she using more of? The $8 bag. Yeah, so counterintuitively, because Karis, I really liked what you said. You'd like to think that she's using more of the 3 to make some profit, but she's actually using more of the $8 bag. And so, maybe she's still eking out a profit. We don't know. Maybe we could call Mavis and find out. But the fact is, when we're all done, the answer should be that we're using more of the $8 per pound bag than the $3 per pound bag. Just a little bit more. Just a little bit more. Okay, so what have we done so far? Talked about Mavis. Talked about the coffee beans. We've just understood the problem. This is a good starting point for any word problem, is just understand what we're talking about. Okay, so now what do? We need to do step 1 and step 2. Define the variables, write our equations. So step 1, define variables. What are our variables? Where do we look? Here we go, look at the question. How much of each type does Mavis use to make 50 pounds of a blend that costs $6 per pound? So how much of each type does she use? So we'll say, let X equal what? Should we say pounds of the $3 blend? So we'll say let X equal pounds of $3 blend. I guess it's not really a blend. We're making a blend. The $3 bean. So then let Y equal pounds of the $8 bean. Okay, so then we need to create our equations. And let's distinguish a little bit about the information they gave us. On the one hand, of course, they gave us the information that it's $3 per pound and $8 per pound. And that will go into our equations. But what are the two fundamental equations that they're asking us to write? In the question, it says, how much of each type does Mavis use to make 50 pounds of coffee? So that's one piece of information to make one equation, the fact that they should be 50 pounds. And then it should cost $6 per pound on average. Well, not strictly average, because we're not adding and dividing by 2. But the blend cost is 6. So that's the other equation. So what's our first equation? Yeah, the first equation, and let's label it. The first equation is the total pounds. First equation is total pounds. So therefore, X plus Y should equal 50. Right? I think it's so helpful to say what you're trying to do, because otherwise you might get stuck in this routine where you just start mashing variables together. Right? It's really helpful if you can actually look at X plus Y and 50 and say, I know what this means. This is the pounds of the $3 bean. That's the pounds of the $8 bean. And together, that many pounds should equal 50. So that the total number of pounds is 50. So then what's our second equation? Our second equation refers to the fact that the cost is $6 per pound. How are we going to do that? So cost is 6 per pound. This one will be a little bit more tricky. How are we tempted to go ahead and start writing this equation? Based on what we've done in the past, what would we start by doing? Yeah, it's probably going to be 3x plus 8y. And why? Why are we tempted to say that? Because it's $3 per bean for the x variable, which is the number of pounds of the $3 bean. And then it's $8 times y, which is the number of pounds for the $8 bean. So far, so good. But we're saying then that it should equal, if we're tempted to write 6, I can see why that's tempting. But is that going to work? That's not going to work. Let's just make up an example. Let's say that we know that it should be slightly more of this one. So since it's 50 pounds, how about just for fun? Let's say that this is 20 pounds and that's 30 pounds. Okay, just for fun, for an example. If that were to happen, then what should we expect? Over here, that would be 3 times 20 plus 8 times 30. And we're wondering, what should that equal? Well, so far that's 60 plus 240, which is 300. So it's $300 that this thing is equaling over here. Now over here, we're trying to say, it should equal the information that it's $6 per pound, right? And what we know for sure is that so far it's $300. That's what this side should equal. Therefore, this side should also equal 300. But we need to write it in such a way that it's 6 times something. And yes, it would be 6 times 50. Because what we're saying is, same as $6 per pound for 50 pounds. So this one was a little more tricky. Let's sit there and look at it and think about it. Whatever this cost is of 3 times x plus a times y, the cost should be equivalent to $6 per pound for the 50 pounds that you're buying. So our equation would be 6 times 50. That's what the equation should be. And it takes a moment to sit there and be okay with that. And notice what we did. In each case, we multiplied the cost per pound times the number of pounds, plus the cost per pound times the number of pounds. And look, the cost per pound times the total number of pounds. And so that might be helpful to write that out. The first number is representing the cost per pound, and that is the number of pounds. And then that first number again is cost per pound, and y represents the number of pounds. And then over here, we're saying that's the cost per pound, $6 per pound, and that's the total number of pounds. And that's how we write our second equation. Questions or thoughts? The other thought we could say to ourselves is, since the first equation is about total pounds, right? The total pounds was 50. The second equation should be about total cost, right? That's another way to think about the problem. The second equation is going to be about total cost. And we could have also thought, well, what is my total cost going to be? The total cost, if it's $6 per pound and you're making 50 pounds, what's your total cost? It's 300. So this is our cost per pound, and this is the number of pounds. And if the first equation is representing the total number of pounds, which is 50, the second equation should represent the total cost, which in this case, the total cost would be 6 times 50, which is 300. So if you wanted to, instead of writing 6 times 50, although that's nice and consistent because it's cost times pounds, cost times pounds, cost times pounds, you could also have just written 300, which was total cost. So there's 2 different ways to think about it. But no matter what, very helpful before you even write down the equation that you think you should write down, is write down what that equation should represent. Okay, so then where does that leave us? We now have 2 equations, right? X plus y equals 50, and 3x plus 8y equals 300. And I think that's as far as I'll go, because now all of you can go ahead and solve that any way you like. You can type it in your graphing calculator by solving for y. You can do substitution. You can do elimination. You could even guess. Well, do you think we could guess? I mean, we know the 2 numbers have to add up to 50. And I tried the guess of 20 and 30. And, oh, in fact, didn't my guess work? Oh my gosh, my guess did work, didn't it? It totally worked. I guessed 20 and 30 by sheer dumb luck, the fact that it was more of that than that. And when I plugged it in, I got 300 equals 300. I guessed the right answer. Everybody, you can go ahead and write it down if you like. So what did I say? The x was 20 and y is 30. That's method number 2.5, sheer dumb luck. Right? That's that method. Okay, so now, yeah, we'll definitely stop there. Everybody, you can use your own method, substitution or elimination, to finish solving that problem. Folks, sometimes I feel a little weird standing up in front of you and saying things like, this is a good problem. This is a good problem. I feel like some sort of like tour guide at a museum where I walk you up to like this piece of art and like it's just a splotch of color and I'm like, look at this really good piece of art. This is amazing. This is beautiful art. And you're like, yeah, that looks like just a bunch of paint on a canvas. But for what it's worth, I'm telling you, that's a good problem. If you can practice problems like that and feel comfortable setting up, converting from a word problem into algebra and then solving and thinking about what the answer should be ahead of time, that's a skill in and of itself too, is thinking about what the answer should be. You know, just by kind of guessing about it. What should the answer be? Okay. Number 15. Everybody ready? Everybody ready. Number 15. Skippy. Who's Skippy? Doesn't that sound like a dog? Or peanut butter? Yeah, I mean, who knows? But Skippy. Skippy has a total of $10,000 to split between two investments. Well, I don't know. I don't know about this Skippy. Where did he get this $10,000? Seems questionable. Just kidding. I'm just playing around, folks. Skippy has a total of $10,000 to split into two investments. So this is number 15. Skippy has 10,000. And Skippy is going to take that 10,000 and either put it into this bucket or put it into this bucket. Well, bucket, investment. Right? So Skippy is going to put the 10,000 into one of two investments. One account offers 3% simple interest, and the other account offers 8% simple interest. So you can already kind of imagine, right? Like if you wanted to use systematic guessing, you could put all 10,000 here, nothing here, or 1,000 here, 9,000 here, 2,000 here, 8,000 here, every possibility in between, including decimals. So he's going to split that money up. For tax reasons, he can only earn $500 in interest the entire year. Okay, so for whatever reason, he's only allowed to earn $500 in interest. So how much money should he put into each account so that he gets the $500 at the end of the year? So what should we do? What's step one? What's step one? Define our variables, right? Let's define our variables. So first things first is define your variables. Define variables. So let's look at the question. How much money should Skippy invest in each account to earn $500 in interest? So how much money should he put in each account? Well, let's let X equal money in the 3% account and Y equal the money in the 8% account. So then step two, create our equations. What would our first equation represent? Keep in mind, we need two equations. There's not a right or wrong answer of which equation goes first, but we are talking about two things, right? Because they gave us information. Notice again, they gave us the account information, 3% and 8%. But what's the other information they gave us? The 10,000 and the 500. So one equation is going to be about the 10,000, which is the total amount of money he can invest. And the other equation will be about the 500, which is the total amount of interest he earns, right? So let's use those words to create our equations. One equation, the first equation, will be total money to invest, which is what equation?
X plus Y.
Yeah, just X plus Y equals 10,000. And then the second equation is going to be total interest earned. And even if we're not quite sure what to write down yet for X and Y, how much interest did he earn? 500. So I really hope this is helpful, folks. In terms of creating a structure in which you can write down equations and feel confident about them, you'll notice that the information they give you ends up being the information that is what the equations are equal to. And by labeling it very clearly, the first equation is the total money invested, which is 10,000. The second equation is the total interest earned, which is 500. So what do we put down for X and Y?
0.03 plus 0.0.
I would agree with all of that except the initial 0. I would just write 0.03 X and 0.08. That's just me. That might be a little nitpicky. I don't put the 0 in front because seeing extra information could confuse someone. Okay, yeah. Now, why did we use 0.03 and 0.08? Yeah. Yeah, the great irony in human existence is we never actually compute with percentages. We only compute with decimals. We only use percentages because the public understands them. You know, we have a gut feeling for what it means, 8% or 50% or 90%. Okay. Now, one thing that we haven't talked about yet is how to get rid of decimals. Right? We all agree it's nice to get rid of fractions. How do you get rid of decimals? You can multiply by 100 because that'll move the decimal point. Like, that's the beauty of the decimal system. You know the decimal system was really only introduced and became widespread in Europe around 1500s. Like, we've really only had the decimal system from like the 1500s on. talk about a recent technology, right? And so the reason we converted to a decimal-based system is so that you can multiply by 100 and just move the decimal twice, right? So if you multiply that whole equation times 100, you really are just moving the decimal twice. So my first equation becomes x plus y equals 10,000, which is still the same. But then the next equation, by moving that decimal twice, so bump, bump, twice, don't forget to move the decimal on the 500 as well, bump, bump. So now we just have 3x plus 8y equals 50000. No, so that's the beauty of the decimal-based system, is that by multiplying by a power of 10, you just move the decimal. But keep in mind, if you did have 0.03x plus 0.08y, you can also just say to yourself, hey, 0.003, that's really 300ths. And 0.08 is really 800ths. And so again, multiplying by the common denominator is 100, and you multiply both sides out by 100. Furthermore, folks, let's just say that you did something totally wonky and you wrote 3% x plus 8% y. Anyone want to go on a limb here? Are you allowed to write that? I mean, have you ever seen anybody write that before? That should look a little weird, right? Because nobody does it. But what does percent mean? What do the actual words mean? Percent. Per means per. But what does cent mean? What does it mean? Yeah, we think of cents as in cents on the dollar, like there's 100 cents in a dollar. But cent, what other words start with cent, folks? Century, which is 100 years. What else has cent in it? Yeah, cents out of 100, what?
50 cents.
Well, sure, 50 cents, and cent means 100 cents in a dollar. Century means 100 years, what?
Centimeter.
Yeah, centimeter. There's 100 centimeters in a meter. What else? Yeah, centipede. Folks, centipede is a hilarious word. Centipede. Do you know what centipede means? First of all, centi means 100, and pede is the Latin word for foot, like pedestrian. A pedestrian is someone who walks by foot. And pede means foot, just like tripod. A tripod has 3 feet. Or a bipedal. We're bipedal because we have 2 legs. Or, well, anyway, so what does centipede mean? It's a joke. The whole word centipede is a joke because the first person who saw the centipede, they were like, whoa, that thing has like 100 legs. Does it have 100 legs? No, it's total exaggeration. So isn't that fun? Centipede. What's the other creature? Other than the centipede, who's the other creature? The millipede. Folks, that's an even bigger joke. Can you imagine the first person who saw the millipede? They were like, whoa, that thing has like 1,000 legs, right? It's a total joke, folks, and this is hilarious. All right, well, anyway, percent means per 100. So watch, 3% literally means 3 per 100, and 8% literally means 8 per 100. And so yes, it's totally legit. You could write 3% x and 8% y, but nobody does it because it looks weird. All right, well, I hope you enjoyed the joke. So there we go. You have your system, and now you can solve it. Now, again, I'm going to leave you there to finish the problem, but I want to work on this third skill that I just mentioned, which is, can we guess which there should be more of, right? So where is he going to put more of his money? Let's just guess. Is he going to put it equal, equal, or is he going to put more over here or more over here? You should be able to do that just by kind of looking at the numbers. So first of all, we need to know how much money would he make if he put all the money in the 3%? What if he put all the money into the 3%? How much interest would he get? Would it be 0.03 times 1,000? Or sorry, 10,000? So how much money would he get if he just put all the money in the 3%? 0.03 times 10,000? Which is 300 bucks. So if he just put all of his money into this account, he'd only get 300 bucks. How much would he get if he put all of his money in the 8%? You'd get 800 bucks. Now, how much interest is he really getting? How much interest is he allowed to get? 500. So what is 500 closer to? Is 500 closer to 800, in which case he's putting more money here? Or is 500 closer to 300, in which case he's putting more money here? What is 500 closer to? 800 or 300?
3%.
Yeah, it's actually closer to here. Just look at the difference. That's a $200 difference, whereas over here, that's a $300 difference. So 500 is closer to 300, which means he's putting more money over here. Does that make sense? Because if he was putting more money over here, he'd be getting money closer to 800. But he's putting more money over here because the amount he's getting is more closer to here. So if we were just to take a wild guess, we're going to split $10,000 between these two accounts, but I'm going to put more money here. How much do you think? Could we say maybe 6,000 and 4,000? Would you agree that that's at least a valid guess? Yeah. Yeah, and this is a good valid thought process. Now, does anyone think that we actually got it right? 0.03 times 6,000 plus 0.08 times 4,000. No. Do you know what it is? That's the answer. Okay, so again, sheer dumb luck. We're just kind of figuring, splitting the money, more money goes here. I just guessed the answer. Now, but I mean, I guess it because word problems are fairly predictable. You know, they're going to use numbers that are nice at the end. So everybody, you can go ahead and jot down what the final answer is. The final answer is going to be x is 6,000 and y is 4,000. I just share that with you so that now you know, and you can do the whole process and feel confident about your answer when you're done. But you still need to sit there and go through and actually solve it. Using substitution or elimination, whichever you prefer. Centimilli. All right. Folks, we are ready for a fun and interesting extension of systems of equations. Once again, what does system mean? Two or more, right? So here's the more. We're now going to look at three equations and three variables. So again, philosophically, you can solve equations so long as you have the same number of equations as you have variables. And here we have three equations with three variables, so yes, we are able to find an answer. Now, just as solve, classify each system as consistent, independent, consistent, dependent, or inconsistent. So, how would we go about solving this? Let's see, where can I begin? I'm going to begin over here. So the equation is 3x minus 1y plus 1z equals 3, and 2x minus 4y plus 3z equals 16, and 1x minus 1y plus 1z equals 5. So let's talk about those methods that we have. What's the first method? Graphing. We can't do that. Desmos doesn't graph three variables. Your graphing calculator doesn't graph three variables. You might be able to find a graphing tool that can do three variables. I'm pretty sure Desmos does not. Like if I just try it out, 3x minus 1y plus 1z equals 3, it says no. So that's a no. We could go to Google and say 3D graphing calculator. In which case, there's a 3D graphing calculator by GeoGebra. This is a good one. So now, isn't that lovely? We have our nice little three-dimensional graphing plot here. And we can now type in 3x. Go, 3x minus 1y plus 1z equals 3. And it graphs a plane, not a line, but a plane. So when you go from 2D, which is a line, to 3D, it becomes a plane. And then we'll graph our next equation. It's 2x minus 4y plus 3z equals 16. Now, do you see the two planes? There's a nice shot of them. Wait. Yeah, there you go. Do you see that they're intersecting? Are they intersecting at a single point? No, they're intersecting it along an entire line, aren't they? It's like the crease where they intersect. And then finally, our next equation is x minus y plus z equals 5. Now, do these intersect at one particular point? I think so. It's kind of tough to tell from this graph. Where do they all appear to be intersecting? I feel like they're all intersecting right there. There seems to be a triple intersection point right up here. It's tough because this calculator is not telling us what that is. But I'd be willing to believe that they all intersect up in that area. Okay? So Now at least you have a visualization of what we're talking about. We're talking about three planes that all intersect at a single point. And unfortunately, this thing is not giving us the answer. I wish it would, but it doesn't. Yeah, I don't. Oh, well, we could graph them with different colors. I don't think that's going to be very helpful. Okay. All right, well, we're done with that. So we're looking for one point in space where they all three connect. So what do? Do what? You certainly could. You could say this is equation A, equation B, equation C. You can do that to keep your work straight. It's not entirely necessary. Now remember, what are we trying to get down to? We're starting with three equations and three variables. What do we want? We want one equation and one variable. That's what we ultimately need, is one equation and one variable. Now, let's just, let's see here. Let's just look at these top two equations. So everybody, you might just want to watch for a moment, and then you'll do it yourself. But let's say that from the top two equations, I eliminate the z variable. Okay, so from the top two equations, let's eliminate the z variable, and what would we be left with? If I add those two equations together and eliminate the z variable, it's not ready to eliminate yet. I mean, look, it's a +1 and a +3. So I didn't eliminate the z yet. Well, let's just pretend I eliminate the z. If I eliminate the z and add these two things together, what would I end up with? Yeah, well, after adjusting for the z variable so that they eliminate, we would end up with something, let's just pretend, with something that says 5x minus 5y equals 19. Okay, we're just pretending that the z is eliminated, right? So if I put the first two together, I get an equation in terms of second two. I don't have another color. Oh, that would have been a long one. Oh, no, I don't. Okay, so then let's say we take the second two equations and eliminate z again. Then what would we be left with? 3x minus 5y equals 21. And so that's our basic method right there, is that we start with three equations and three variables, put the first two together to eliminate z, put the second two together to eliminate z, and now what do we have? Just a normal system. Two equations and two variables. And at this point, if I change all the signs on this first one, minus, plus, minus, I can now eliminate y and get down to 2x equals -2 and finish solving the problem. Nothing about that answer is correct, because we didn't actually eliminate z correctly in the first place. I was just showing the flow of how that would happen. So to solve a three-variable system with three equations, you would just buddy up the first two equations, get rid of z, buddy up the second two equations, get rid of z, and now you've reduced the problem to a regular two system, a two equation system, which you can then solve the normal way. Now once I have x, how do I solve for y? I go back here, plug in, solve for y. And then once I have x and y, how do I solve for z? Go back to one of those and plug it in. Okay, so that's our method, folks. Everybody ready to try? Everybody's super stoked? So here's what you have to do. Again, let's take these first two equations, and let's come on over here, and we're going to write down the first two. This is going to take a lot of space, by the way. Don't you have the whole page? Yeah. I mean, this will take a good amount of space. So we write down our first two equations. So 3x minus 1y plus 1z equals 3, and 2x minus 4y plus 3z equals 16. What's our goal? Yeah, let's eliminate z. Now, why did I choose z? That was a totally arbitrary choice. I could have eliminated x from the first two, eliminate x from the second two, and then get a system in y and z, and then continue from there. I just randomly decided, let's get rid of z. So if I want to get rid of z, this is a positive 3z. I wish this were negative 3z. So I'm going to multiply the whole top equation by negative 3. Don't forget to distribute all the way. You have 4 terms now. So that's negative 9x plus 3y minus 3z equals negative 9. All right? So you have to distribute that negative 3 all the way across to all 4 terms. Now I created a situation in which I have a z with a 3 and 1 plus 1 minus. That way the z's cancel out. And now when I add these together, I get negative 7x minus 1y equals 7. And what is that? It's an equation in 2 variables instead of 3. That is just one little step on our long journey to solving for all three variables. Now what do we do? Now what do we do?
Take your second step.
Take the bottom two equations now. So now I'm going to take my bottom two equations and do the exact same thing. With the bottom two equations, I'm now going to eliminate z again. So I'll take my bottom two equations, which are 2x minus 4y plus 3z equals 16, and 1x minus 1y plus 1z equals 5. And then once again, I want to eliminate z. So as always, you look at the larger number, positive 3z, and so I wish this were a negative 3z. So we'd multiply that whole bottom equation by negative 3. Once again, distributing all the way across, remembering to multiply every term by negative 3. Which would give us negative 3x plus 3y minus 3z equals negative 15. So right now my eyeball would have to jump up and down between the top and the bottom equation. That's too much work for my eyeball, so I'm just going to rewrite the top equation right next to the equation I just generated. It takes, a couple extra seconds of work to do that, but that way I can clearly better see what's eliminating and what I'm getting. So that's negative 1x minus 1y equals 1. So now, again, philosophically, what did we accomplish? We started with 3 equations and 3 variables. I now have 2 equations and 2 variables. And now what am I going to do? I'm going to take my 2 equations and 2 variables and do elimination again to get down to 1 equation and 1 variable. So I'm going to write those down. Negative 7x minus 1y equals 7. And negative 1x minus 1y equals 1. Quite the process, isn't it? I didn't say this explicitly, but when you're solving systems of 3 equations, I think elimination is the best way to go. Substitution would be wild. You'd be making a substitution sentence with 2 variables in it. Ooh, that'd be something fun you could try at home by yourself. When you go home later tonight and you're like, gee, I just have absolutely nothing to do. No work, no homework. I'm going to solve this using substitution. Okay, what variable would you like to eliminate? X or y? Y would be easier because it's already negative 1y. I wish that were a positive 1y. I can go ahead and change all the signs, right? That's a valid method. You can either multiply all the way by negative 1, or you can just say, hey, I'm going to change all the signs. So now my y cancels out, and I have 6x equals negative 6, and x equals negative 1. Now notice how far we are from home still. Like, we're still on a huge wing and a prayer that that's even correct. We could have made 7 mistakes at this point. We could be completely off. But we have no choice but just to continue, move forward, and start back substituting. Okay? This process that we're about to do is called back substituting. We are going to back substitute all the way back through the 2 variable equation back to the 3 variable equation. So we now have x. Now what's our goal? Maybe we should write this down. Our goal is to have an x equals, y equals, and z equals, which forms a triple coordinate, a coordinate in 3-dimensional space. Right? We're looking for a coordinate in space that all 3 equations intersect at. And so we need to solve for x, y, and z. So far we've solved for x. So what should we solve for next? The other variable from our 2 variable equation. So which equation do you want to plug into? Negative 7x minus 1y equals 7 or negative 1x minus 1y equals 1? I'd probably do this one. Just because there's no 7 in it. It looks a little easier. So I'm going to back substitute into negative 1x minus 1y equals 1. And I'm plugging in for x, so that's negative 1 times something minus 1y equals 1. And what are we plugging in? Negative 1. So now we have 1 minus 1y equals 1. Subtract off the 1. Ooh, negative 1y equals 0. And dividing off the negative 1, y equals 0. So far we have x equals negative 1, y equals 0. And we still need to solve for z. So how do we solve for z? We come all the way back here. Which equation should we plug into? Sure, we can do the bottom one. We could do the middle one. We could do the top one. You can plug it into any of them. But yeah, probably the bottom one, Josh. Why? Yeah, it's got the smallest coefficients. Probably the easiest to plug into. So now we're going to plug into x minus y plus z equals 5, where x we know, y we know, and z we don't. So x was negative 1, y was 0, and now we just need to solve for z. So it's negative 1 plus z equals 5, and then add the 1 over, and we get z equals 6. So our coordinate, apparently the coordinate in space where they all intersect is negative 1, 0, and 6. So it's a three-dimensional coordinate in space. Where those three planes, remember they were planes, where those three planes intersect. Is it right? No, we don't know yet. We're not done. So now we have to plug all that in. Well, plugging in negative 1, 0, and 6, fortunately the 0 is pretty easy. Because when we plug in 0, all these terms just go away. Right? So now we just need to plug in negative 1 for x and 6 for z and see if the remaining equations are true. So if I plug in negative 1, 3 times negative 1 is negative 3 plus 6. Negative 3 plus 6 is 3. There's 1. Here, 2 times negative 1 is negative 2 plus 3 times 6 is 18. Negative 2 plus 18 is 16. That worked. And then 1 times negative 1 is negative 1 plus 1 times 6 is 6. Negative 1 plus 6 is 5. Yay! Now the problem's done. The problem is all done. We found 3 numbers to plug into the 3 equations that make them all true. Have you ever done anything like it before? Maybe not. It's quite the process. Look again, philosophically, what we did. We started with 3 equations and 3 variables. And we just buddied up 2 of them to create 2-variable equation. And we butted up the other 2 to create another 2-variable equation. Now I have 2 2-variable equations, which I then put together to eliminate again to get a 1-variable equation. So that gave us 1 variable. We back substituted it into one of our previous 2-variable equations to get our 2nd variable. And then we back substituted both of those into any of our original equations to get the 3rd variable. Yep. Now, if you've never done that before, that probably felt a little overwhelming. So what should we do? Cry? No. Try again? Yeah, we should try another one. Not cry, try. That's what we should do. So let's look at that second one. Now notice, this second problem is even easier. Why is this one easier? I didn't hear any of that. Say that again.
One of the equations is 2 variables.
Yeah, one of the equations is already 2 variables, right? Isn't that our goal? We want to go from 3 equations and 3 variables to 2 equations and 2 variables. And they already gave us 1 equation and 2 variables. So that kind of tells us what we should do with the other 2. So what variable did they not have here? Y. So let's take the other 2 and eliminate the y. Because that way we would have 2 equations and 2 variables. So I'm going to write this down as number 2. I already like, I'm going to write down, I like the 10x minus z equals 2. I like that one because it's already 2 variables. So now what I'm going to do is take the other 2, which is 2x plus 3y minus 1z equals 1, and 4x minus 9y plus 2z equals 5. And remember our goal, we want to go from 3 equations and 3 variables to 2 equations and 2 variables. I already have an equation and 2 variables, so I need to create another equation and 2 variables. Which variable do I need to eliminate? I want to get down to another equation that has x and z. So I need to eliminate the y. So looking at y, I want to eliminate y. This one is negative 9y. Again, always look at the bigger one. So that's negative 9y. I wish this were Positive 9y. So I'm going to multiply that whole top equation by 3, distributing all the way across. So that gives us 6x plus 9y minus 3z equals 3. And then that will eliminate the 9y. Giving us 10x minus 1z equals 8. Ooh. Hi there. Can I help you?
Can you come in and photograph?
Sure.
All right. Is this math or biology?
This is math. Oh, watch, she's going to change her mind. She doesn't want to bother photographing math.
Okay, we're using math.
Now, who are you? How do I know you're not loiterers?
You know I'm not a lawyer. I'm in marketing.
Oh, okay.
Yeah, and then some history folks from.
Gotcha. Folks, they say they're from marketing. Should we believe them? They have a badge. Yeah, come on in. Yeah, I have a badge too. No, I'm kidding. So what are you taking photographs for?
Marketing purposes,
Okay.
advertising purposes, yeah.
Okay.
It's our Make It Happen campaign.
Oh, nice.
So you guys are making it happen, so.
All right. Now, does everyone have to sign a waiver? Is that what's happening?
Yes, so.
Okay.
That's what they are?
Pictures of them.
So folks, you have a choice. You can be in this photograph or you do not have to be in the photograph.
Yeah, if you don't want to be, just,
Yeah,
we'll.
you can totally just go stand back at the back of the room. You're still required to do math, but you can just go stand in the back if you like. Ironically, I'm not going to sign the waiver, so I'm going to go stand in the back of the room too.
Awesome. So these will be used in like print ads and on our web banners, all over.
Now, folks, keep in mind, these very generous folks from marketing are paying each of you $10
Yeah, no.
to be in this photograph. That's an amazing opportunity. Send the appropriate thank you letter.
Is everybody over 18?
They would say I might not act like it.
Okay. All right, good. All right.
Excuse me, why do you want the cell phone and the email?
In case we have to get in touch with you again.
Oh, here, it's with,
Yeah, they could be like, hey, that shot of you in that math class was so amazing. We want to put it on a billboard on the freeway.
All right. Have you done this? No, I mean, everyone has the releases, but I have not taken pictures of them. Just sign. Try not to be too disruptive. So what level of math is this?
This is mat150. College algebra.
Yeah, you have yours open?
Oh.
it's just hard for us to see it, that's why I was passing out. There you go.
Oh, yeah, that's right.
Yeah, or open here on the side. It's big, so you can see it.
I don't recall seeing. But maybe there was an accident. I do, I would do.
And write it really big, guys.
What was the
Friday, not Friday, Friday before, and then sent another one.
Okay.
3 weeks.
I'll check.
But
All right.
that's okay, you can do it.
Okay, I think we're almost done filling out our forms. Then we can go back, finish this problem.
All right.
First, do I have to fill out a form?
No, you're an
Oh, I'm an
employee.
employee.
You have no rights.
Oh, well, yeah, I have no rights. She's not joking, folks.
Okay, you need you to hold it and then you have to take a picture to make sure release. Yeah, it's, I just like, sorry.
That's funny.
Good.
shot phase 2.
All right.
I think that you just sign your paper there. But then just use your photo. And then-
You got all this side?
Guys, yeah, yep. Yep.
Would the subject line have been photo shoot?
Yeah.
Really?
But I don't have.
All right, so we're good.
We're good.
Okay,
Sure.
all right.
Would it
you're
be
good.
from you?
Okay.
Is that CH?
CHR, 224,
CH, I'm sorry, what? CH?
R, 224,
CH or 224?
or.
Okay. I mean, but that's from March 6th,
Yeah.
if that's the most recent one.
That's
Okay.
Yeah.
Yes, maybe not.
Yeah.
Is there any more pens?
The practice. Yeah, I didn't see it. Okay, everybody ready? I think we're all set with the forms. We can keep doing some math. Now, folks, what did we just find out? We took our 3-variable equation, or 2 of our 3 variables, and eliminated the y, and we got? Yeah, we got 10x minus 1z equals 8. That's wonderful, because the other equation was 10x minus equals 2. So already just looking at that, you might already predict what the answer is. But now, to finish the process, you take your 2 equations in 2 variables, 10x minus z equals 2, and 10x minus z equals 8. And again, let's just say we wanted to finish the process. Which variable do you want to eliminate? You can eliminate either one. We can eliminate z. So this is a negative 1z. I wish that were a positive 1z. So you can either multiply through by negative 1 or just change all the signs. I'm going to put negative 1 there and then distribute. So now I have negative 10x plus 1z equals negative 2. And then that eliminates the z. It also eliminates the x. And we're left with what? False. So again, it's as if we shouted out the question, where do these 3 equations intersect? And the answer comes back false. They don't. Yeah, they just don't. So you would say false, never, they don't. Now, what does that mean exactly? Because we just looked at this graph. We just looked at the graph a moment ago, and we all clearly saw that they did intersect. I mean, look, we've got 3 planes. They're all intersecting. So what does this now mean that the math is telling us, no, they don't all intersect? What are they specifically saying about the fact that they don't all intersect when we can clearly see with our eyes that they all do intersect with each other? What are we saying? They don't all intersect at one spot. Yeah, there's not one point in space. And yeah, I kind of felt that way the first time we looked at this. I couldn't see clearly one spot where they all intersected. And that's because there isn't one spot where they're all intersecting. So that's the end of our problem. The solution is there is no solution. And let's be very specific as we write down that answer in a sentence. The 3 planes do not intersect simultaneously at one point. All right, that's the key. We were looking for one point, x, y, z, where all 3 planes went through. So what does that mean then about the truth? Is there a coordinate that I can plug in to make all three equations true? Is there one coordinate that I can plug in to make all three equations true? No. I could probably find a coordinate that will make two of the equations true, but then the third one would be false. I could find a different coordinate that would make two equations true, but then the third one would be false. So the best that we can do with this system is that I can probably make two of the equations true, but then the other one is going to be false. So we're never going to have a point of triple truth. The point of triple truth won't exist. Okay. So that was a nicer problem, huh? We didn't have to go all the way through to the end. But on the other hand, you know what I would do with this problem that you did a moment ago, number one? I would go home and do it again. Right? Just take out a sheet of blank paper, write down the problem, and try it again. And you can always refer back to your notes. But I would try that one again. Now, fortunately, we do have another three-variable, three-equation problem to try, and it's a word problem. So everybody, let's turn the page, and we get to practice both. We're going to practice turning the word problem into equations, and we'll practice solving those equations. Now, you folks in the back, just so you know, I saw them. They took a picture of all of you in the back. They're like, look at all the people sitting in the back. I'm just totally kidding. They didn't do that. That'd be mean. Okay, number 5. Let's take a look. First of all, these word problems follow upon what we just did. So we're predicting that it's a 3-equation in 3 variables. That's what we'd expect right now because that's what the other problems were. So let's take a look. And infirmary, what's that? You know, some sort of hospital or nurse's office. It's a place where people go when they're sick or wounded. I normally hear about an infirmary like in a war show. Like they get sent to the infirmary. Okay, so an infirmary has solutions of 10, 30, and 50% alcohol content. I'm assuming that's for washing wounds, right? We're assuming that it's for washing wounds, not for drinking. So we have an infirmary with 10, 30, and 50% alcohol content. Let's start by drawing a picture right there. What we have is a bottle, and that's 10% alcohol solution. And then 30%, that's another different bottle with 30%. And then another bottle with 50% alcohol solution. And again, they're probably all for washing wounds. So a nurse needs 20 liters of a 40% alcohol solution. So how could we get a 40% alcohol solution? Let's just look. We have the ability to pour a little bit of this, pour a little bit of this, pour a little bit of that, and we want to somehow end up with a 40% alcohol solution. Let's just make the problem simple. What if I only had a 10 and a 30% solution? Could I pour those together and mix up a 40% alcohol solution? What do you think? Can you mix a 10% solution with a 30% solution and get a 40% solution? No, that's not possible. Yeah, because anytime you mix a 10 and a 30% solution, you're going to get something between 10 and 30, right? So if I mix 10 and 30 together, equal parts, what would I get? If I did equal parts of 10 and 30 together, what would I end up with? 20%. Wait, that's 20%, right? Because 10 plus 30 would be 40, divided by 2 is 20. So if I just mix these together, I'd get 20% in equal parts. But no matter what, I'm going to get a number between 10 and 30. So if I only had these, could I mix a 40%er? No. You'd have to get some more alcohol somewhere to add some more alcohol into that. So no. What about just these two? Could I mix these two to make a 40%? That would work, and very easily too, huh? Because how much of each would I need to mix to get 40%? Yeah, I could do equal parts. And if the nurse wants, what, 20 liters? I could just do 10 liters of this and 10 liters of this. Again, this is pretending I don't have this bottle. Okay? So if I just had this problem, that problem would be very easy to do. If the nurse wants 20 liters of 40%, I could do 10 liters of this, 10 liters of this, and then I'd be done. Right? So what makes this problem tricky? That apparently we need to use all 3 bottles. Now, I don't know why that is. I'd probably write the nurse and be like, hey, just use the last 2 bottles. That's much easier. But apparently the nurse wants to use all 3. Maybe we should finish reading the problem. So a nurse needs 20 liters of a 40% solution. Let's go ahead and say we need 20 liters. And therefore, again, we're thinking like, 5, 5, and 10 maybe, or 2, 9, and 9. Who knows? We just need some combination that adds up to 20 liters. So how much of each solution is needed if twice as much of the 50% solution as the 30% solution is used? So for some arbitrary reason, we're saying that we need to use twice as much of this as we use this. Right? Now, what would that even look like? If I need twice as many liters here as here, Let's actually list out some possibilities. What would that look like? Let's say I used 1 liter of this. How much would I need here? 2 liters, right? Because you want it to be twice as much. Or let's say I use 2 liters here. How many liters would I need of this? 4. Well, let's say I use 3 liters here. How many liters would I need of this one? 6, right? So does everyone feel comfortable with just the examples? We're saying that how much of each solution is needed if twice as much of the 50% is needed as the 30%. So now, just for fun, let's call this x, y, z. We haven't defined our variables yet. But if we say this is y liters, then how many liters do we need here?
2y.
Yeah, 2y, right? So right now we're still just playing around. We're just trying to understand the problem. So then if this is y and that's 2y, this would be whatever else. Yeah, we can call that one x. And then I would know that x plus y plus 2y should all add up to how many liters? 20 liters total. Okay? So that's all we know so far. Do we understand the whole problem? An infirmary has solutions of 10, 30, and 50. A nurse needs 20 liters total of the 40%. And how much of each solution is needed if twice as much of the 50% is used as the 30%? So that's what we know so far. Come on back, folks. Thanks. So folks, we are going to finish this problem. So what I'm going to do here is just make a little arrow that says here twice as much. Okay. So we've thought about the problem. Let's finish setting it up. What's step 1, Chelsea?
Label z as 2y instead of 2z.
Well, what we're saying then is that z is equal to 2y. That's what we're really
Instead
saying.
of having 3 variables, it would be.
You're going to end up with 2 variables. Yeah. Okay, so folks, step 1, by the way, just so you all know, I took pictures of them. I'll show them. No. Okay. So step 1, we need to define our variables, right? So what are our variables? Now keep in mind, let's say that you can't even finish solving this whole problem. If you at least define your variables, you're showing good faith, right? Like, don't encounter a problem like this and leave it blank, right? Because you can at least take a good step, a good faith effort, and say, well, let x equal the number of liters of 10%, and let y equal the number of liters of 30%, and let z equal the number of liters of 50%. Right? Believe it or not, see, in mathematics, even if you don't know how to solve the whole problem, if you just start writing things down that you do know, you might actually surprise yourself and baby step your way to the answer, right? By just starting somewhere. Okay, so that's step 1. Those are our variables. What's step 2? We need some equations. So what are our equations? It says the nurse needs 20 liters. So what's one equation? Step 2, first equation is the total number of liters, right? So what's that equation? Now, do you folks notice that we almost always have an equation that's just x plus y equals something, or x plus y plus z equals something? Okay, so what's our second equation? The second equation is, what do we know has to be true?
X plus y plus 2.
Well, we don't know the 2y yet. And it won't even alcohol content, right? Then somehow it should end up equaling the fact that it's 40%. So let's look here. What were the alcohol contents of each variable? So it'd be 0.1x plus 0.3y plus 0.5z. And then the whole thing should end up being, and this is just like the previous problem, we already know that the very final solution should be 40% and it should be 20 liters. So that means it should be 40% of 20 liters. And notice again, this is very consistent. This is percentage times liters, percentage times liters, percentage times liters, and the final mixture should be a percentage of 40% and the total liters of 20. Okay, so that's an equation. Where do we get our third equation from? The only other piece of information they gave us was the fact that you should have twice as much of the 50% as the 30%. Which means whatever number I put here, this should be twice as much, and therefore z is equal to 2y. And that's our last equation. Z equals 2y. This is a very different type of equation, or a very different type of system. Because normally we're used to something plus something equals something. But right now they're just telling us, hey, by the way, z equals 2y. So what do we do with that? And I know that I have to finish here, but I want to get you in a position where you can finish solving the problem. What do we do then? We know that the first equation is x plus y plus z equals 20. But what did we just say z is equal to? 2y. So I can change that and write x plus y plus 2y equals 20. And after I combine like terms, that's really x plus 3y equals 20. There's my first two-variable equation. Because remember, philosophically, we're going from three-variable equations. We need to get down to two-variable equations. Okay, and then what about that second equation? Now, first of all, nobody wants decimals, right? How do we get rid of all those decimals? Multiply by 10. So move the decimal once, move the decimal once, move the decimal once, move the decimal once. So that new equation would be 1x plus 3y plus 5z, and then moving the decimal on the 4 times 20 is 80. So that's what that equation would be once you move the decimal once. But we still want to substitute out the z, so z is actually equal to 2y. So that would give us 1x plus 3y equals, or sorry, plus 5 times 2y equals 80, which is really 1x plus 3y plus 10y equals 80. Which is, combining like terms, that gives us 1x plus 13y equals 80. Okay, and now look what we've accomplished. We took our original word problem. We just spent some time understanding it. We've defined our variables. We wrote down our equations. There were 3 equations they gave us. And remember, we want to go from 3 variable equations to 2 variable equations. By substituting in z equals 2y, we were able to change both of our 3 variable equations into 2 variable equations. And now that we have two variable equations, what do? Yeah, solve like normal. You know, whatever method that is for you. You can solve by substitution. You can solve by elimination. Probably elimination would be pretty easy because they both have a positive 1x. So we can eliminate the 1x pretty quickly. Should we do that? I know that I'm already begging your time here. I realize class is over. But I'm going to go ahead and just finish it. So if I have 1x plus 3y equals 20, and then the other one is 1x plus 13y equals 80, I need a plus 1x and a minus 1x. So again, we all know now that you can just change the signs on the whole equation. So that's really a negative 1x minus 13y minus 80. And that gives me negative 10y equals negative 60. And divide out the negative 10. And apparently y is equal to 6. Oh, we're going to finish this problem, folks. The answer comes so quickly now. If we know that y is 6, what does that mean z is? 12. So now we know y is 6. We know z is 12 because it's twice as much. And the total number of liters is 20. And this is already 18. So the last one is x equals 2. Now, are we done? Definitely not. For all we know, we're completely wrong about everything. We made so many mistakes, we have no idea. But if we plug in 2, 6, and 12, I already know the third equation is true, because z is twice as big as y. But we still need to plug in, oh, and the first equation is true, because they add up to 18. So we really just have to check the third equation, or the middle equation. So that'd be 0.1 times 2 plus 0.3 times 6 plus 0.5 times 12. And it equals, oh my gosh, it's correct. It's 8 equals 8. Okay, let's do the next problem. All right, I'm just kidding. Everybody, you should be able to now finish all of your homework from 8.1 and 8.2. Because we didn't get to 8.3, we'll start that next time. But you should now be able to approach the homework in 8.1 and 8.2. So, what is today, Wednesday? No, it's Monday. Well, in any case, go ahead and start working on 8.1 and 8.2. I don't think you have anything due tonight, do you? Oh, just 8.1?
There's no 8.2 on the.
There's no 8.2, yeah, just 8.1 then. Yeah, you're right, just 8.1 is due tonight. Thank you, folks. You all deserve a snack.
It's due tonight. So just 8.1 is due?
Yeah, I think just 8.1 is due tonight.
There's 2.
I don't think anything should be due tonight. I'll go ahead and change the due date so that nothing is due tonight. But you should all work on it tonight.